Okay, one more try. If I don't do it, I'm gonna have to give up. No diversion. I've been trying to make this video. First try was sometime, about 24 hours ago, where I discovered a cute little thing, and I wanted to make a video to show it to you, to anyone who might want to watch. What was that beef about? This doesn't beep. Now it's a C++ thing. And I assume that you've programmed in C++ if you've never seen one of my videos before. They're about C++ language, and often kind of esoteric topics. Often the topics might be difficult, but I try to explain them in as simple a way as possible. In this case, the topic is one that is a subtle one, a subtlety, and the sort of hack solution is also maybe a little bit difficult to understand, but I'll try. First, let me just see if this works. And I'm going to let you observe if it does. Diagram. I just created from YouTube. What comes first, on or off? Maybe it doesn't really matter, does it? Off. Maybe on, I think, definitely comes first. 1080p. Append. Off 1080p. This one. Ah, gosh darn it. Now, what's going on with this? Audio stream. It can't be different. $128. Hang on a second. Mistake. Just a minute. It worked. Okay. That's great. All these files you gotta make to make one thing. You need enough space for all these temporaries. Okay. This is what I'm recording. This goes, where is it going to go? Temporarily. In documentary. I already have it, but this was higher quality. Where is it? I have it somewhere. Okay. Now, here's the thing, a thing about C++ that you probably know, and probably bugs you. Here's a typical structure that one might come up with. Like, for instance, my editor. It's a thing that maintains a file, right? Maybe a file name. I almost diverged there. I have a way to turn one of these into one of these in mind. A buffer with some data, a size, actually that's included here, but whatever. Rectangle for the window position. Maybe there might be a cursor position. Who knows? Now, C++ was born C, And so this struct idea was already known and being used, and people love the idea. And C++, one of the intentions of C++ was to extend this struct concept and add a little bit more flexibility to it. For instance, to be able to declare a struct and not have to initialize all of the data, every time. You could invent, if you could invent a function that you would pass it. That's what people used to do, is invent a function, declare a struct, pass the pointer to the struct to a function which would initialize all the variables, and that was essentially the idea of the constructor. Instead of having to invent a function that takes a struct, you make it a member of the struct, and then initializing the structure is simply a matter of declaring it. It's already initialized. Syntax is great. Now this particular constructor that doesn't take any arguments is called the default constructor. All this applies, of course, to classes, struct, with the default being private. Everything here is public. Now, because of the way that C++ is designed, that the possibility, not the possibility, the fact of the ability to create more than one constructor for a struct automatically exists, because a function and its type and everything are part of its name. So therefore, it would be possible for me to make another constructor for my struct here. Let's say I might have one that takes a regular string, file name, and let's say perhaps a limit to a limit on how many bytes from that file we'll read in. Let's say so. It could be a uint or keyword or long. Actually, it's probably best. L max size to read limit upper limit. So either that means that we're not going to open files that are bigger than this limit, or it means that for a given file we'll only load this much, perhaps at a time. It could be that our struct, like the hex editor, might cache, instead of reading all the data, it might just cache a certain amount, right? Plus or minus so many bytes. Okay, now so instead of calling this file size, we'll call this max file size. Now, sizes are typically in unsigned, represented as unsigned numbers. However, you'll notice that I chose a signed value for this limit. The reason for doing that is because a lot of the functions that deal with moving around a file, okay, like fseek, this function fseek. You see what it takes as a parameter? A long, right? And that's because you can go you can seek in the plus direction or the minus direction from whatever your origin is. Well, a function like this can only support a file whose size is at most a 31-bit number, right? If you're going to be able to go, I mean, the size itself could be larger than that, larger than it could, well, it could be a 4 gig file, but you wouldn't be able to seek from the beginning to the end. You'd have to go halfway and then again go another half, right? It's much simpler if you just limit the size that someone can pass in by making this signed, right? And then your seeking is easy. You just use whatever number is passed in and the direction or whatever, and you can't go wrong. So that's why I would choose a long here. However, I would store it as an unsigned value, and well, there's 2 ways to do this. And whenever you see that there are 2 ways to do a thing, you should stop. And I'm telling you now, you ought to stop and ask yourself why. I'll do it one way, and well, first I'll do it the function way, if you like, which is to just assign mdw max size this, right? Now I can, of course, I can add an assurance here that this value should be less than long max, right? Let's say right? Less than, I think, is best. You wouldn't want anything to be equal to the limiting to the maximum possible value, right? Because of the possibility of adding 1, right? Or the possibility of testing if something is bigger than, nothing can be bigger than long max in terms of longs, and so typically it's a good idea to restrict your values to being strictly less than the maximum. So long max minus 1 for the size. Now this would return and nothing would happen in this case. Now file name. I would just set my file name variable here. Okay. And again, you might have an insertion here. Not empty string. You have a macro for that. Checks if it's null or if it has, or if it's empty. Okay. Now, well, that's not the best test, but it's close to what you would do. Alright, now here's the problem. What about all this other stuff? You know, how do I initialize all these things? I don't want to type that down again. Well, the answer is, sorry buddy, you gotta type it down again. So you gotta type all this down again. Kinda sucks, doesn't it? And what if you forget, you know, to type it down again? I mean, wouldn't it be great if you could just sort of say, you know, please run this function first, and then I'll go on and change these things only. They don't allow that. Then I think the new C++11 has fixed this problem and come up with a solution, an even better solution than what I have. In the language, you can combine constructors in a very flexible way. Even the things that you're derived from, you can selectively choose which, I don't know how it works, but I saw something about it and it looked great. But I'm poor, and that's why the intended title of this video was The Mother of Invention. The mother of invention being, I think as the saying goes, necessity. If you're poor, like I am, and you can't afford to go out and buy the latest compiler, you might try to invent something like C++11 with tricks. Now the trick I'm going to show you is kind of a hack trick. But nevertheless, it's kind of an interesting curiosity, at the very least. Now it all came about because of that hex edit, which isn't in here anymore, which led to this delegate thing, and the inner and the outer, uncle inner and anti-outer. And I noticed something, and I think I mentioned it in an earlier video, to do with that inner outer thing, the delegate thing, that has a function called uncouter. And I said something about, I don't think the compiler will allow you to access the outer classes members in the declaration statement because it's still building the class, even though the compiler should know at least everything up to where you've made your declaration. Have I got it here? No, it's in here. Okay. So I was just thinking about this. Forget about the delegate thing. Don't need it. It's in the history. Now, I was thinking of inventing a function, a struct, calling it default constructor. Let me hide the details. And it would be like this. Call it CTOR or something. And as a member of this struct, there's a function called it doesn't have to be called that, but that's what I called it for the other thing, and that's what gave me the idea. Okay, this here is a member of this struct, right? Okay. So therefore, if I give this thing, this member of outer a constructor, give it a constructor, right? Then while the construction process is proceeding, this constructor will get called at least for any constructor that the outer class has, the constructor for this object will get called. Okay, during the process of construction and before you get to these put functions, right? Okay, now that's where I started to wonder. Well, it's true. What if I called that uncouter from inside here. Am I going to get the right answer? That's one question. If I called this function, is it going to give me the pointer to the the struct of which this thing is a member? And the answer to that question is has to be yes, right? Because if you think about it in terms of the compile, since this is returning a pointer, the compiler doesn't need to resolve this, right, at compile time. And the implementation will be compiled properly when the compiler gets to the implementation line for this. So therefore, at runtime, when this gets called and I call this uncouter, the uncouter has, written into it, into the binary code, the information that can locate this, the pointer to the containing class. It has to work, right? It's just a matter of me knowing my own offset, which I know at this point, this here is valid inside here. So I can call that is valid, right? As a valid function call, and there's nothing ambiguous about that. And within here, the compiler has already computed the distance from here to here, and so this function must succeed. Now if we call again, that this function is getting called somewhere along here, okay, before the entry into this part for all of these functions and the default, right? And that function which is being called before outer has been constructed, knows this pointer of outer. Like this would be invalid, if I wanted to say something to do with this. I couldn't do this, for instance. I hate the word this. I'll get in trouble if I tried to do that, because the object hasn't been constructed yet, right? And I think the compiler would complain even if I tried to do that. Will it complain? Let's see. Just curious. I don't think it will even allow me to do that. Enough brackets. But in any case, this is the outcome of this expression is not deterministic. Oh dear. Gotta return something. And that's in utest. I'm not even looking at utest. Oh, I don't have this on. Sorry, utest. Interested in this project. This is not a well-defined statement because the order in which these things are actually constructed It has nothing to do with the order in which they're written out here, even though some people will tell you that will tell you that I'm lying. They would be wrong. Here, see, it's a warning. This pointer used in the base initializer list, not allowed. Or you're allowed, but it's undefined behavior. I'm going to demonstrate to you, by the way, just so that you believe me, that this ordering has nothing to do with the order of the constructing of these objects along after the colon. But that'll come in there. Okay. Now, here's the outline of my special default constructor that always gets called for every constructor. It has a default constructor called default. Its name is default constructor. Maybe I should give it a better name. Defcon, defctor, defcon, def. How about that? Or that? You're not allowed to use underscore. I'll choose this. I don't want to use that because that word is used internally as well. I don't want to get confused. Now, so this constructor is going to get called all the time. And what I would like to do is initialize the outer class by calling the outer class's default constructor from here. So therefore the default constructor will get called for every new constructor, and you don't have to write all that stuff down again, right? Okay, how would I do that? Let's implement it here. First, there's a problem of recursion. Okay, like if I call the default constructor, right, for this outer class, so that by default is going to call the constructor for this thing, right, and I end up in a recursion loop. So I would like to not have that happen. So I'd like to know if I've already done this. If I've already done this, then don't do it again. And the way to know if I've already done that is to see if I'm being called. If this call is re-invoking this function. So I would like to have a way to determine that. Now initially, my method, which is not 100% guaranteed, was I added another variable here, which is a pointer variable. Okay, and inside here I set that equal to my this pointer, and then I check to see if this variable is equal to my this pointer, and then if so, return. However, that's not a guarantee because this thing has its value is random. It could be any value initially, and it might accidentally, 1 in 4 billion chance, it might actually be equal to the value of this pointer for this object. So instead I found I worked very diligently and came up with another method to do that, where it doesn't rely on luck. It required a few extra functions. First, what I'm looking for is I want to walk the call stack and try to see if this function init outer is currently being executed, and if so, I want to return. So here's a Boolean function called by self, and it returns whether or not I happen to be already inside this function. If I am, then I return. If not, then I run the outer's default constructor. Okay. Now, how does this work? Simple stack walk. Using the TS_address class, which has functions such as this. Actually, I made this one up just today. I think there's a compiler intrinsic called not address of caller, but there's return address, but that's not the same thing. Right? That doesn't give you a function position, it gives you a return. I don't know, I could check, but I'd rather do it myself. Address of caller, it's funny the way it worked out. See, initially, this had this name, address of current function, and it took an argument for how many steps back you want to go. But instead I called this one address of caller, and so it returns, with no arguments, it returns the address of the function which called your function. Going back here, that means that this address should give me the address of the function that called this function, so it should return to me the address of this init outer. If it works, and how it works is now I have to draw a picture or something. Imagine we have one of those constructors, something, and that is calling the inner things, defcon, what do I call it? Defcon, its constructor, right? Whoops. Def cthor. Boy, I would get that wrong. No. Right. There's a constructor here, and it's calling one of the member variables constructors, because that's how constructors work. And within this constructor, this is calling a function called init outer. Now that's the name of the class. Right. No, really, there's an outer in front of all of these, but well, maybe I can drop it. I'll drop one name. We'll assume if it's indented, I'm going to leave it in here. Right? Now this guy wants to know is asking the question called, am I calling myself, right? And the question is done through a function call. Now I have to make sure. Now I think one can be sure. You want to make sure that this thing actually turns into a function, right? That the optimizer doesn't turn it into a macro, because this thing is examining the stack and so on and so forth, right? This function called by self there has to be a call to a function. I'm not sure what you're supposed to specify, but there's something you can specify to make sure that a function does not get inlined, as they say. The code doesn't get inlined, a call occurs. Call occurs, and so here we are in called by self, which is supposed to tell this guy whether or not he's being called by himself, right? So what does this thing have to return? Well, let's imagine the case where a recursion has occurred. So now that would mean this, say, return false. So this thing can return true. How do you do that? Let's say that this thing returned false. It figured it out somehow, returned false. So now it returns, and this guy is going on to call the default constructor of outer. Or outer, sorry. Like this. Okay. Alright. Now that brings us back up here again, right? How do I draw that quickly? It would be better if I used an editor that has column editing, but I can do this pretty quick. Thing. That was fast. Okay. Okay. Now we're in here a second time. Back into the default constructor for def ctor. Who calls init outer and wants to know whether or not to go this way or to return. So now this function has to return to this function whether or not this has occurred, right? If this has occurred, that means that on the call stack, if you walk backwards from where we are, right, then we find ourselves on the call stack. If we can only get the function that called, find out a way to find out what the calling function is, and then we got it, right? And that's what this thing has to do. Now, in order to find out, in order for this thing to find out the function say that called this function, it would have to find this function's return address, which is here, right? And find out where that instruction jumps to, and then it can locate the position of this function, right? If it wanted to find out the function that called this one, it has to go back to here, right? And find out what this function is calling, right? And that would be the caller of this function. You've got to go back to, remember, a call. It's like E8 and then a 4-digit number. Something like that. This is the anatomy of a call. I think it's E8 or E9. Could be not. One or the other. And the way it works is this is a assigned integer value, because calls can be in a positive direction or negative direction. So the maximum length of a call is long max, as it turns out. Another reason to think long max. Okay, now it's possible to determine the address of this position. Let's call it RR for return. This is called the return address for the function. For a given function, how do I make a up arrow? I don't have anything. It doesn't matter. This here is the position that is stored on the stack when a function call occurs. The function might be here, some function. Okay, not even on the same line. Actually, we'll put some numbers underneath. Here's foo, and over at foo here, the first byte is either a 55 or C8 or something. 55 is push BP, but whatever. Some more instructions and so on. On the stack, the address of RR here is given. If we go back 4 and read this number off, right, then the position of where foo is, call that CC, or call the called function, the call, result of the call, is this position, not the return address, but return address minus 5. Oops. Right, plus whatever this evaluates to should give you this, turns out. Oh no, maybe it doesn't include that, because if you put all zeros here, right, then that will take you to this position. So a 0 takes you here, so therefore this from here to here is this number. Okay, so this distance we'll call that number jump, something like that. Okay, so we look on the stack, we find the return address, we subtract 4, read off that number, and then starting from here, add that number, and that gives us the address of this function. Now this guy wants to know initially, this function initially wants to know what function called me, right? First thing, because that's the one he's concerned about. So how is this one going to get the address of the function that called it? Well, he can get his called by self, could be foo, and can get his return address, right? But all that's going to tell called by self about is where the beginning of its own function is, right? That's not what this question, that's not what this thing wants to know. It wants to know the position of this function. So in order to get the position of this function, it has to go and find the function that called this function, this one, take that address, and add this value, and that will give called by self the address of the function that called it. Alright, long-winded explanation. Now, that's what this is doing. I call it address of IO, not IO. It's init outer. I should call it address of caller, but I think I can call it that. So the address of the caller, the one that called this, yeah, I'm just using this function. How's the function work? Going back here. This thing here first computes. No, remember now we've called another function. You know, it's now this guy wants to find out about this, and so it's calling another function, address of caller. Let's put it down more. I will. Because it's a general purpose function, I need a general purpose thing. Alright, now this guy would like to tell this guy which function called it, right? So it has to go all the way back to here, 3 steps back, right? And find out the call position, the final call result for the instruction that called this function. And so it has to step back through the stack frames 3 times, read off this number, add that to the position of the return address of this function, and that will give the value of the function that called the function that's calling this function. Okay. Now a number is passed in. 0 is wouldn't be to return to the caller. The address, the one I just explained. So now there's a +2 here. Return address +2. Return address gives me the address of the function that called this function. So return address points to a position within this function somewhere, not this function itself, but a position in there. That's of 0. Return address of 1 would give me a position somewhere in here, and 2 in here. So that this here puts us in the right area. We're somewhere in here. Now, this I've called address POC, address of the point of call. The return address is here. The point of call address is here. I've gone a long time. I'll have to split this up. Okay, this is stuff that I went over a long time ago, but it's easy to forget. I had to refresh my memory. Here's this address is the point of call, which is 5 less than where the return address is. Okay. Now I don't even know if I use this, but I wrote it down here just to. Oh no, I do need it. This here checks to see if at address point of call, if we can read 5 bytes. Is it readable memory? If not, then fail. So we didn't find anything, right? It doesn't mean we should crash. It just means that address is not pointing to somewhere valid. The address on the stack. Okay, otherwise, if we can read it, to get the address, we're looking for the address of this function, right? To get that address, we have an address in here, which is of this form. I mean, that's in a situation of this form. So we add 1 to the point of call position. And I'm just casting this to a keyboard so that I can later turn this into an int. So first I cast this to a pointer to constant void. This could also say constant, whatever. And now I'm casting that to an int star and dereferencing it, and that gives me a number which is an offset. Okay. Now I would like to find out the address that was called. That is, what address is this plus jump? And that's exactly this. Here's return address, RR, and here's jump. Add those two together, and that gives me the address that the instruction calls. However, these instructions don't typically call functions. In fact, jumping, if I run it, if it's compiled and running, I can show you. What they tend to call are these things called ILT, I think, or FLT, something lookup table. Okay, let's see. As an example, before going through it slowly, here's the actual call stack. Okay. Address. I've computed an address in the manner I showed you, and I've just computed something called address called. Okay. Now this thing is actually telling me what that is, but let me do it a different way. The number is 401136, right? See, this here is not a function at all. It's a jump. It's a jump. So that's not the address of any function. It could be interpreted as such, but it's not actually the address of a function. And it doesn't. Sometimes you see these characters ILT or something, but whatever, it doesn't matter. So what I really want to return to the caller is the address of the function that called the caller, right? Not the address of some position in a table, because that's of no use. It's not the only way to get to the function, right? So so I have this function, I had it already, that resolves the any jumps that might be intervening in the call, and gives you the final address where the function is. That goes in here, and it also tells you, I can get rid of this last thing because there's only one possibility. Now again, we're dealing with address minus 5. What did I pass in, by the way? The thing passed in is a return address, okay, an address that was computed as being called by that at that return address, or the instruction before it, and it's going to verify that is true, right? That everything is fine and correct, and tell us where the final location is. Okay. I used to have a bunch of comments, but they're all gone. Now, the first thing it checks for is that the return address passed in. If it's a call or a jump instruction, and that is these are the two instructions. One of them's call and one of them's jump. I forget which. Okay, and the destination address has to either be a function, right? A function entry point, which is characterized by a 55 or a C8, okay? Or it could be a jump, as in the case that we're looking at. It turns out it was a jump. It's going to be an E9. Get rid of the source code. No, not source code. Code bytes. E9. See? So if it's an E9, then that's valid. If it's neither of those three, then there's something wrong and it's not verified. Okay. Those succeed. The dest opcode E9 is a jump instruction, it turns out, and we're trying to find the final address after any jumps. There might even be 2 or 3 jumps, who knows. It might jump from one table to another table. So what this thing does is just keep going along as long as we're getting jumps until we get to an enter function. Okay, we got 55, that's correct. That means push EBP. So we found the final address, right? The way the jumps work is the same way that a call works. It's a signed integer value relative offset. So we're just what I've done here is computed the final address by taking the current final address and adding this as if it were an integer plus 5, because there's always that additional 5. Right? This number doesn't count from here, it counts from here, the next line. Sorry, here. Okay, so the final address turned out to be that, and this is useless. It's always going to be E8. This assertion has never gone off. I don't allow anything else, right? But I got to get rid of that. It doesn't matter. But it was verified. Okay, so now we're going to return that address, and the address of the third function backs position of call, destination, final destination is this, which is outer def tour init outer. So the address, the address of the function that called this function is in fact this, and the answer is correct. Now we're doing a stack walk. We have the address of the caller. If we find any more of these addresses on the stack, right, then we're in a recursion. Otherwise, if we hit a dead end, then we're not in recursion, and it's okay to proceed. Now, well, I've taken way too long. I'll continue this in the next video. Okay, so I'll stop here and let you have some time to think about this, and I'll continue on from here. See you.